right, so we're on page 57 and we're looking at Dalton's law. I think you guys learned about Dalton's law over Christmas. Yeah? Okay. So we have the total pressure is equal to the pressure of all the gases in the system. So if you have gas A, gas B, gas C, or gas 1, gas 2, gas 3, the total pressure is equal to the partial pressure of each gas added together. Is good? Okay. Now, I'm going to flip over to the PowerPoint, if I can find it, because it shows this as like a little animation, I think. Let's see, yes. Okay, watch our video here. Oh, why is it so small? It's not small, it's good. Okay, so Dalton's law. One of the simplest gas laws, it says for a mixture of gases, the total pressure of gases is the sum of each of the gases' partial pressure. There we are. Watch as we fill a large gas flask with 2 gases. So here we go, we're going to add the red gas. Whoop. Goes up to 3 atmospheres. And then we're going to add the blue gas. Whoop. Up to 5.3 atmospheres. Pressure of the first gas was 3 atmospheres. The total pressure was 5.3 atmospheres. What was the pressure of the blue gas? 2.3. Yes, indeed. Okay, so there's our equation. We substitute those in and we get our pressure. Okay, so that is just, the pressures were also directly proportional to the number of gas molecules. There were more molecules of the first gas, so that's why its pressure was greater than that of the second gas. Dalton's law is used another way, and this is what we're focusing on because the rest of it was just review. It's sometimes very difficult to measure the volume of a gas. You can't just pour a gas into a graduated cylinder, right? Like, because it would just escape, it would run away. And it's already filled with a gas. It's got air in there already. So how can we get around this? The solution is to fill the graduated cylinder with water, turn it upside down, and then add the gas. Now you can just use a graduated cylinder, but we can also use a gas collection tube or a gas measuring tube. They do come specifically for the purpose. And here is a little simulation of what happens to measure the volume of a gas produced in a reaction. We will be measuring the gas produced by the heating of potassium chlorate. So there's our reaction. Potassium chlorate breaks down into potassium chloride and we produce oxygen gas. So we'll be looking at how much oxygen gas is being formed. So here's our setup. We have our test tube and we have this is called a eudiometer or a gas collection tube. And then we have a container full of water. There's our gas measuring tube, the eudiometer. A substance that produces a gas is placed in the test tube. So there is our potassium chlorate. The eudiometer is then filled with water. Bloop, 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 bloop. Then we stopper it. Boop. We turn it upside down and put it into the water. Then, under the water, so this requires getting your hands wet, you remove the stopper. So now you have this tube, and you connect a hose from the test tube that contains the stuff that's going to react. There goes the hose, it gets fed under and up. Again, you're getting your hands wet, and this is going to allow the gas to move into the eudiometer. What's that, sorry? It actually doesn't because the test tube is above the water level. The water will only go up to the level here, right? It won't actually, it can't move up just because of gravity. So it'll only go up to about here in the tube. Now we're going to heat it. Here comes our Bunsen burner. The substance is heated. Oh, look at those bubbles of gas. There we go. And what's happening at the top of the tube? We have gas collecting, okay? And it keeps going. There we go, more gas, more gas, more gas. And there we are. Because the water level inside the tube is lower than the water level outside the tube, what does that tell you about the pressure inside the tube as opposed to the pressure outside the tube? Yeah, it's greater because it's pushing down harder. So what we want to do is we actually want to make those two pressures equal, because we know the atmospheric pressure. We can get that from a barometer. Okay, and so we want to know what the pressure is inside the tube, which we will get from the atmospheric pressure by making the two equal. How do we do that? We raise the tube until the two water levels are the same. And now we know that the two pressure, the outside pressure, the atmospheric pressure, is the same as the pressure inside the gas collection tube. Okay, if the water level had been higher inside the gas collection tube, we would then add water to the whole system, okay, into this beaker or, you know, whatever it's called, like a trough. We call it a pneumatic trough, okay, full of water. We would add water until the levels were the same. So basically we have to, the key thing is to make the two water levels the same. Water in the tube and water out of the tube have to be the same, or we can't do the calculation. Then we use the little markings on the tube to measure the gas volume inside the tube. And we also take the temperature of the water, because that's going to be important for our calculation later. And this all sounds good because now we have a volume, we have a pressure which is equal to the atmospheric pressure, and we have a temperature. Pressure, volume, temperature, we could in theory figure out the number of moles, yes, of the gas. But here's the problem, the gas was not pure. We were producing oxygen gas, and you would think that it was only oxygen gas in there. However, if we are collecting over water, what does water do? It vaporizes. So we have the vapor pressure of water in there. So we've got water gas and we have oxygen gas. So this is where Dalton's law comes in, because we can figure out how much water there would be, okay, and then we can subtract that using P total equals P1 minus P2. So the total pressure of the two gases is the same as the outside atmospheric pressure. That's why we equalize the pressures by raising the measuring tube. The pressure of the water vapor depends upon the temperature of the water, and you can actually look that up on a table. It will usually be given to you in the question. The vapor pressure of water at this temperature is blah, blah, blah. Okay? The warmer the water, the more water evaporates, the higher the vapor pressure of water. So we consult our table. It says it's at the back of the book, but it's not at the back of your book. I presume I've put it in there somewhere in your actual book. So here we go. So you would pick, if we were at 15 degrees, the pressure would be 12.8 millimeters of mercury. That would be the pressure of water vapor. So if the atmospheric pressure was 755 millimeters of mercury that day, and the temperature of the water was 25 degrees, we can say that our total pressure is the oxygen pressure plus the water pressure. So we can substitute our total pressure, the atmospheric pressure, PO2 plus PH2O, and then we can go look up the vapor pressure of water at 25 degrees. So we go look that up. There it is. Pressure of water is 23.8 millimeters mercury. Pop that into the equation, and guess what? We just solved for pressure of oxygen. So now we know the actual pressure of the oxygen. We know the pressure, we know the volume, we know the temperature, we can find the moles. You can also use Boyle's law to figure out the volume of dry gas at any pressure. P1V1 equals P2V2. So there's our pressure. That's our volume of the gas in the measuring tube. There's the volume of the gas at pressure 2. Did I actually put this in here? Sorry. I don't know how much of I did in. Let's go back here. Okay. Hey, where's the rest of it? Okay, so all of this was just what we did. And then there's some exercises. Do you want to do some exercises? Might as well, because that's it for this, really. It's a fairly straightforward topic, but people often kind of just forget about it, so a little bit of practice will not go amiss. So yeah, try a couple questions, and then, yeah, we'll see how far you get, and that's how much I'll assign to everyone for the week. Yep, so it's all up to you. Oh, there you go, and then there's nothing to do.